Hello, everyone. My name's Noah, and I'm going to be talking about our work on streaming and sketching algorithms for symmetric Boolean constraint satisfaction problems. And this is joint work with several collaborators, Joanna Boylan, Michael Huang, Tarun Prasad, and Santoshini Velusamy. And I was mostly working on this when I was at Harvard. I'm now a PhD student in the computer science department at Carnegie Mellon. So this work is sort of at the intersection of two major areas of theory, one being combinatorial optimization and the other being algorithms for big data. And I'm going to start by defining the models for the problems and for the algorithms and talking about the history of people who have worked on things which are at the intersection of these two areas. I'm going to talk about our specific results and give a self-contained example for a particular CSP. And finally, I'm going to discuss sort of further technical details and some future directions, which I think are interesting. So maybe a helpful example to keep in mind as we set up the sorts of things we're looking at is the streaming version of the max 2and problem. So in this problem, there's constraints, which are ands of two literals. And think that the constraints are coming really fast and we don't have enough memory to store all of them. But our goal is just to say estimate how many constraints can be satisfied by the best possible assignment to the variables. And we want to understand when is this possible in the setting where, again, we don't have enough space to remember all of the constraints that we've seen. Okay, so more generally, we can think about constraint satisfaction problems that are parameterized by a predicate, which takes k bits to 1 bit. So these constraints then just take the predicate and apply it to a set of distinct literals, which either look like a variable or the negation of a variable. And then an instance consists of a list of constraints along with non-negative weights for those constraints. Now, we can consider what happens when we assign each variable to a bit, either 0 or 1. The value of that assignment is the fraction of all the weight in the instance that is satisfied by this assignment. And finally, we can define the value of an instance as the highest value that any assignment has on that instance. Okay, so because we don't even have space to remember all of the constraints that we've seen in the settings that we're going to be considering, we settle for solving a slightly weaker problem than calculating the value. We want to estimate the value. So given an instance, we want to output some estimate, which is an underestimate for the value, but not by a factor that's worse than alpha, where alpha is some constant that's between 0 and 1. So in this setting, there's a notion of what it means to trivially approximate the value of an instance. And that is when our estimate actually doesn't depend on the instance at all, just say on the predicate that we're using. So you can check that the best possible trivial approximation is just to randomly assign every variable uniformly to 0 or 1. And the expected value of this assignment is the same as just the probability that a uniformly random k-bit string satisfies the predicate. So the question is, in one of the models that we're thinking about, can we beat this? Can we, say, get a constant approximation that's better than this trivial threshold? We denote the trivial threshold by rho. And so, for instance, for the k and problem, the trivial threshold is 2 to the negative k, because a uniformly random assignment will in expectation satisfy 2 to the negative k fraction of the weight of the constraints in an instance. Okay. So the particular types of algorithms that we're thinking about solving these problems are streaming algorithms and a subclass of streaming algorithms called sketching algorithms. So a streaming algorithm somehow models doing some computations on really big data sets. And there's two properties that the streaming algorithm is required to have. One is that it only uses a sequential pass over the data. The second is that its space is bounded. And we'll talk about what sort of space bounds we're interested in soon. But first, I want to mention that there's a subclass of streaming algorithms called sketching algorithms, which I'm not going to give a formal definition, but roughly, this just means that the algorithm can't depend on which position in the stream it's at. So if it sees an element, it has to treat it the same, regardless of whether, say, like this element is a constraint. So the constraint is showing up at the beginning of the stream or in the middle of the stream. It has to treat it the same way. Okay, so in this work, we're thinking about streaming algorithms and sketching algorithms, which are trying to estimate the value of an instance of a Boolean constraint satisfaction problem. And their input is the stream consisting of constraints in the instance in some order. Okay. There are also some more sophisticated models allowing like multiple passes or particular orderings of the constraints, but those are out of scope for this paper. Okay. So to give a brief history, in 2015, Koprolov, Khanna, and Sudin studied the max 2 XOR CSP, which is probably the simplest Boolean CSP, and they show that there is no non-trivial approximation, at least if you're looking at streaming algorithms which use less than square root n space. In contrast to this, in 2020, Cho, Golovnev, and Santoshini, my collaborator, showed that there is a non-trivial approximation for the max 2 problem, which I would say is the second simplest Boolean CSP. So in particular, they proved an upper bound and a lower bound. The upper bound showed that if you're looking at any constant which is less than 4/9, you can get an approximation with that factor in log space streaming, log space sketching setting. But if you want to get a approximation factor which is a constant better than 4/9, you can't do that with sub square root n space, even if you're using a streaming algorithm. Okay. So this shows somehow that like the right threshold that determines whether you can approximate this max 2n problem in the streaming setting, at least if you're looking at log space versus square root n space, is 4/9. And building on this, Cho, Golovnev, Sudin, and Velusamy proved a dichotomy theorem that looks like this, but holds for all predicates. And I'm going to talk about this in the next slide. But first, I just wanted to mention there are many other works that have considered other variants of these sorts of problems that I'm not going to talk about sort of for the rest of the talk. Okay. So what does this dichotomy theorem that I talked about on the previous slide actually say? So Cho, Golovnev, Sudin, and Velusamy proved that for every predicate that takes k bits to 1 bit, there's some approximability threshold such that you can, for any constant less than the threshold, you can get an approximation in logarithmic space sketching, but you can't get any constant better than that with sub square root n space sketching. And there's two things to note about this. Firstly, so we know that you can get a trivial approximation, but they show as a corollary that this threshold alpha can't be better than twice the trivial approximability. So alpha is sort of between these two extremes. Secondly, generically, their lower bound only holds against sketching algorithms, not streaming algorithms like in the 2 and case that I showed on the previous slide. However, under certain technical conditions, which I'm not really going to get into, they do show that this lower bound can also rule out alpha plus epsilon approximations with streaming algorithms. Okay. Another property of this dichotomy theorem, which is important, is that it doesn't give a general procedure to find a closed form explicit expression for alpha, although maybe you can like sort of approximate it to arbitrary precision. Okay. So I just have one slide sort of summarizing the results. So the overall thing that we try to do in this paper is calculate this approximability threshold for a number of constraint satisfaction problems. So the sort of canonical problem that we're thinking about is the max kn problem, and our results are new when k is at least 3. So again, the trivial threshold for kn is 2 to the negative k, so twice the negative threshold, twice the trivial threshold is 2 to the negative k minus 1. And we show that when k is odd, the actual threshold that you can get is basically this upper extreme 2 to the negative k minus 1 times some discounting factor, which goes to 1 as k goes to infinity. And something similar happens when k is even. You basically get twice the threshold for the next odd predicate. And something that's interesting about this is we show that, you know, our result implies that you can get arbitrarily close to 2 to the negative k minus 1 in like a multiplicative sense as k goes to infinity with a log space sketching algorithm. But recent very strong streaming lower bounds due to Cho, Golovnev, Sudin, Velusamy, and Bellinger show that you can't beat this 2 to the negative k minus 1 by any additive constant, even when you go all the way to sublinear space streaming algorithms. So this gives like a very sort of sharp trade-off for how well you can do with a sketching or streaming algorithm, and shows that this 2 to the negative k minus 1 is at least asymptotically tight. Okay. We also have some other results. We show that these technical conditions that give streaming lower bounds don't suffice to resolve the approximability even of max 3 and. in CGSV 21. And we also give simple explicit algorithms for a number of CSPs like max KN. So actually the next thing that I'm going to talk about is a simple algorithm for the max 3 AND problem. And you can throw away everything that I've said in this talk so far, more or less, and I should still hopefully be able to convince you that we can get some relatively simple algorithm for the max 3 AND problem that beats the trivial approximation factor, which is 1/8. So to begin, I'm just going to talk about some quantities that we can associate to variables and to instances of max 3 AND. So for each variable in an instance, we can define pos of I as the weight of all the clauses that contain a positive copy of x sub I. So by this, I mean just x sub I without a negation. Similarly, we can define neg of I as the weight of all the clauses that contain a copy which is negated of x sub I. And then we can define the bias of the ith variable as the difference between these two quantities. So to interpret this, if a variable has high bias, if a variable has positive bias, that means it occurs, you have to take into account weighting, but it's basically saying that it occurs more often positively than negatively. And if it has negative bias, then it occurs more often negatively than positively. And the magnitude of the bias says sort of how much xi this variable cares. If the magnitude is very large and say the sign is positive, that means this variable is almost always occurring positively in constraints. So we can also sum up this bias over all the variables. And I'm just going to define a normalized version where we divide by the total weight in the instance. And we sum up the bias at really the absolute value of the bias. And this gives us a number between 0 and 1. And the key insight due to Guruswamy, Velinkar, and Velusamy for 2017, at least in the setting of 2 AND, is that, okay, firstly, we should expect a positive correlation between the bias of an instance and its value. So why does this make sense? So these are both numbers between 0 and 1. So let's imagine we have an instance where the bias is really close to 1. So what this means is that basically all the variables occur almost always positively or almost always negatively. And what this means is that it should be hopefully easy to assign the variables to a bit like based just on the sign of their bias. On the other hand, if the total bias is close to 0, that means most variables occur roughly evenly sort of between positive and negative occurrences. And this may mean it's hard to find a good assignment and that the value is low. Okay. And the second key insight is that this bias just corresponds to like a normalized L1 norm of the vector of all the biases of all the variables. And when we see each new constraint in the stream, we can think of that as doing like a, say, +1 to the bias of a certain variable and -1 to the bias of another variable. What that means is that we can measure this bias quantity up to some additive factors using standard techniques from the sketching algorithms literature, like these L1 norm sketching algorithms, which were originally due to Indic. Okay. And I just want to mention at this stage that this CGSV 21 dichotomy theorem roughly says just that this is the optimal way for every predicate that you could try to get estimates using sketching algorithms. You should just estimate this bias quantity. Although this is maybe not quite true. Okay. So now I'm going to present a simple algorithm for the max 3 AND problem. Okay. So imagine we have an instance of max 3 AND and consider the assignment Z that does the following. It's a random assignment. If it sees a variable that has non-negative bias, it assigns it to 1 with probability 2/3 and 0 with probability 1/3. On the other hand, if the bias is negative, then it does the opposite. It assigns it to 0 with probability 2/3 and 1 with probability 1/3. Maybe why this makes sense is that like if the bias is positive, it may still be small in magnitude. So maybe we're not confident enough that we want to always assign it to 1. We just want to assign it to 1 with some probability sort of bounded away from 1/2. And the theorem is that this is a good assignment. So the expected value of this assignment is at least 2/9 times the actual value. So we get a 2/9 approximation. So 2/9 is 0.222, whereas the trivial threshold is 1/8, which is 0.125. So this is actually much better than the trivial approximation. And then I'll also show sort of along the way that like the value of this assignment, expected value, is also lower bounded by some quantity depending only on the bias. So if you look at this quantity depending only on the bias, it's at least 2/9 times the value, it's at most the value. So that means this quantity also itself gives a 2/9 approximation to the value. if we were trying to implement this as a sketching algorithm. Okay, so I'm going to prove this to you. So to begin, I just want to define some notation. Let P of t denote the fractional weight of all the constraints in the instance that have t positive literals. So we have like P0, P1, P2, P3. And our goal is to express important quantities like the value and the bias in certain ways, like with equalities or inequalities with linear combinations of these fractions. Okay, so one thing which is helpful to define is a signed variant of bias. So remember when we defined bias before, we had like absolute value signs around the bias of each variable. Now we just drop the absolute value sign. And this gives us a signed total bias, which is between -1 and 1, and which is upper bounded by the bias. Okay, so if we double count, we can show this linear expression for the signed total bias in an instance. So for instance, if we look at a constraint which has 2 positive variables and 1 negative variable, then this will contribute sort of +2 to the biases of the 2 positive variables and like -1 to the bias of the negative variable, and altogether, the net impact on the signed total bias is to increase it by 1, and then we normalize, so it will end up being 1/3. So we get this expression, and then since we know that all 4 fractions, when we add them together, we get 1, and we know that the unsigned total bias upper bounds the signed total bias, we get this inequality that 1 plus the total bias is at least some linear combination of P1, P2, P3, and that equality holds if and only if the bias and the signed bias are equal, which is happening if and only if all variables have positive bias. So let's say that an instance has property A if all variables have positive bias. So as we said in the previous slide, property A implies that we have an equality that 1 plus the total bias equals this a linear combination of P1, P2, P3. And I wrote the coefficient on the previous slide as 2, but now I'm going to suggestively write it as 6/3. So I also want to note that if we have an instance which satisfies property A, then the expected value of this random assignment can be also expressed as a linear combination. Why does this make sense? So every variable occurs more often positively than negatively. So it has positive bias, which means Z is assigning every variable to 1 with probability 2/3 and 0 with probability 1/3. So for instance, if you have a constraint where all 3 variables occur positively, so all 3 literals are positive, then it will be satisfied by this assignment with probability 8/27, because you need all 3 variables to be assigned to 1. You do linearity of expectation and you get this formula. So then the thing to note is if you compare this term by term with this, we have a 2, we have a 4, and then here's an 8 and here's a 6. So we can actually prove an upper bound that this quantity, and if we divide by 9, is at most this quantity. So we get a lower bound on the expectation of the value of this random assignment. Okay, what about an upper bound? So from a few slides ago, we also had this no longer with an equality, but now we have an inequality that this 1 plus the total bias is at least this linear combination. So let's assume that our instance has a different property, which we'll call property B. If it's the case that the optimal assignment for the instance psi is just to assign every variable to 1, then the best, then the value is just equal to the value of the all ones assignment, which is just equal to the fraction of constraints where all 3 literals are positive. Okay. Again, doing a term-wise comparison with this, we conclude that the value is at most half times 1 plus the total bias, because here, if you do a half, then this becomes a 1. The coefficient of P3 here becomes a 1. Okay. So again, we got this lower bound on the expected value of this random assignment by some function of the bias, and we also got an upper bound on the value by a function of the bias. But a priori, these only holds, like the first one only holds when the instance satisfies property A, the second only holds when the instance satisfies property B. But the punchline is that if we take an instance and we flip the signs of some of the variables, so like the literal x1 becomes not x1 and not x1 becomes x1, this preserves the value, the bias, and sort of the expected value of this random assignment Z, sort of by definition of these different quantities. So what this means is that both these equalities actually hold without loss of generality. And so the expected value of the assignment is lower bounded by 1/9 times 1 plus the bias, and this is lower bounded by 2/9 of the value, which means that in expectation, this random assignment gives us a 2/9 approximation to the best possible assignment, which, as I said, is non-trivial because trivial will be 1/8. Okay, so now I just want to quickly discuss what happens when we generalize the reasoning in the previous section to other predicates aside from 3 and what this has to do with some future directions that seem interesting to work on. So very roughly, what the dichotomy theorem says for a general predicate f is that to calculate alpha, first, this is sort of standard in the literature on hardness of approximation, you reduce to thinking about these gapped problems where you're trying to understand whether it's hard to distinguish between instances that are value less than beta and instances that are value greater than gamma, and then you're looking for the smallest ratio that you can get between beta and gamma. And then, very roughly, what it says is that this beta gamma problem is hard to solve if and only if there's two instances which somehow fool bias-based algorithms, which somehow look like the algorithms that we were looking for at 3 and in the previous section. So these instances like sort of have the property, like in this no instance size of n, every variable is positively biased, and then every assignment that assigns each variable to 1 with some probability and then 0 with 1 minus that probability has low value. And on the other hand, the value of the yes instance on the all ones assignment is high, and then these two instances have matching signed biases. And somehow this is like the right notion of fooling the algorithms that we were talking about in the previous section. So unfortunately, when you're trying to apply this characterization to actually calculate the ratio alpha for general f, it seems to be difficult. So firstly, this expected value of the random assignment is a degree k polynomial in the probability that you assign each variable to 1. So if you want to find alpha, you need to like maximize a degree k polynomial, which already it should be impossible to find an explicit form for the maximum once k is at least 6. And then you need to optimize the ratio of this lower bound with an upper bound over instances with matching sign bias. And this in general seems difficult or impossible beyond very simple cases like for 2 and where k is 2 and then CGV actually found explicit solutions. So in our paper, how I sort of like to think about it is that what we show is that for many different predicates, such as 3 and, it suffices to think about only a single random probability that you assign, each variable to 1 if it's positively biased. So in the 3 and section, we were able to get a good algorithm using the same probability, 2/3, for assigning positively biased variables to 1 for every instance. And somehow this corresponds to doing something like a max-min inequality when you're trying to calculate alpha. So like alpha will look like the min over some beta gamma thing of the max over p of something, and this corresponds to using the max-min inequality and doing first a max over p and then a min over everything else. And we show that for many predicates, this will actually be sufficient to give a tight bound on alpha and calculate alpha explicitly. And so how we actually go about this is we numerically estimate p and then the corresponding yes and no instances, psi y and psi n, and then we guess the correct closed forms and then do the analysis. And if our guesses are right, then the analysis should just become some sort of term-by-term comparisons of linear expressions like we were looking at in the 3 and section. So two sort of interesting future directions that I am sort of thinking about. One is, so we show that 2/9 is the sketching approximability threshold for max 3 and, which means you can't do better than 2/9 with sketching algorithms in sub-squared n space. So it would be amazing to show that this holds for streaming algorithms. And in fact, as I sort of mentioned a little bit back, we provably show that the CGSV21 lower bound techniques can't prove this conjecture. So we need new lower bound techniques if this conjecture is true, or who knows, maybe there's a streaming algorithm which isn't a sketching algorithm, which gets better than 2/9 approximation for max 3 and. And the other thing which would be nice is to get a more systematic understanding of when this max-min trick, where you consider a single random assignment probability for all instances and get an optimal result, is adequate for characterizing approximability. And in fact, in the paper, we proved that for certain other predicates, it's not sufficient. So it would be nice to have like an understanding of when it is or when it's not sufficient. Okay, so thanks first to Madhusudan, who supervised everybody who was working on this project, and then thank you for listening.